RTD, Resistive Thermocouple Devices. What are they? It's a little bimetal piece of material that goes on the end of some kind of computer sensor, some type of computer analog to digital conversion device so a computer can read it. It's the only thing you can do with an RTD, Resistive Thermocouple Device. And it really is as simple as taking two pieces of dissimilar metal and stamping them together at the end. And because they're dissimilar metals, when you heat or cool them, they'll have a reaction to it at the boundary of those two surfaces. Really interesting, amazing stuff, right? Resistive thermocouple devices. So, what is that? That's your digital thermometer that you use for cooking. A lot more accurate than trying to read the dial indicators we used to have, or having to stick the thermometer in there. And then you go back and you remember when thermometers had mercury in them. That little bit of mercury is enough to poison the minds, the bodies of quite a few people. So we stopped putting mercury in thermometers. Good idea. People thinking. Evolution. Scary word. So this RTD idea. I'd been introduced to them because I sat on a bench calibrating the instruments that might use an RTD device, or calibrating even a thermometer, a mercury thermometer, certifying its accuracy, and what it says and tells you is accurate to some good percentage, some proven percentage. So that RTD device, in this example, there's 1,000 of them taped all across two reactors, exothermic reactors, very high temperatures internally, making plastic, a third of the world's plastic, to be pretty precise. So these thermocouples sitting out there glued onto the side of a huge pressure vessel wandered. The readings from the computers were all over the place. That caused $1 million in fallout from that instrument not reading well. One of them was the instrument design engineers went out and reviewed field devices and learned the thermocouples weren't terminated properly. These are very precise devices, and if you don't terminate the ground for the shield wire that runs out the length of that thermocouple device, might be, 1,000 feet, 30 or 40 meters away from the data collection panel, the computer that's servicing all those RTDs. So one of the problems was drift. Another problem was the instrument just going crazy. It was figured by the electrical engineers that the ground fault loops caused, the ground loops created by the wrong termination at the reactor end, which means to fix this means removing possibly, layers of insulation, shutting the reactor down, cooling it enough over days to be able to work on. So those things aren't taken lightly. They get planned and scheduled in. But the symptoms didn't match what the instrument was doing. So one of the thoughts was the eddy currents caused by this bad termination of thousands of I/O points might be causing the instrument to malfunction internally, causing a glitch on a bus or a backplane. So we went through the routines, the EMI, RFI, noise isolation and reduction and things like that. But in my gut, I knew it was a software driver in one of the end modules that talks to the thermocouple scanner, because I could watch the scanner directly with an instrument for days and it just worked like clockwork. But I was seeing drift in the thermocouples because of termination problems, but it wasn't an instrument failure problem. So what it ended up being is a device driver inside what's called a process control module, which if you're a controls person, that would be comparable to a PLC type of thing, only written in software and not machine ladder logic. So these RTDs get scanned. Now why did I even bring this up? Well, that RTD puts out a number. It doesn't put out a temperature. It doesn't say 57 degrees. It puts out a number between 0 and something. It actually puts out a voltage. Or it causes a differential in an applied voltage, to be a little more specific, but a little too close to the physics of an RTD device. Lots of videos out there, you can go find them on. But so again, we're scanning thousands of, or over 1,000 thermocouples on 2 reactors. Got redundancy, so there's actually 4 computers out there scanning these with a split load on the thermocouple devices. There's redundant process control module, that's like the PLC thing I talked about, that's talking to that, and then that passes through to a display control and a supervisory control system. So big integrated systems tied together, talking to a little thermocouple out in the field. Now this did cost $1 million in the end. The issues that surrounded this and the reactions to it. And if I had gotten what's called a data analyzer, network sniffer, much earlier in the process, I could have pointed to really the root problem quicker. So this is one you have to know about: electronics, computers, RS-232 communications in this case, thermocouple communications, device scanning. So inside of that RTD scanner, the thermocouple scanner, is A to D, analog to digital converters, because they're going to take that little voltage off their thermocouple device and turn that into a number. That number gets passed back to the computer, and the computer says, oh, that number is 75 degrees, or 380 degrees, or 720 degrees, whatever the temperature is on the thermocouple that it's capable of measuring. So now we just converted that analog signal, that little DC voltage change that you get from the thermocouple device, into a number for the computer. The computer is going to tag a time with that too. Now we've got the data set we're going to go log somewhere, and we're going to display to the operator, and we can go see the history of, for histograms, we can do predictive analysis based upon process settings that made changes. So that simple little temperature measuring thing turns into a whole setup for manufacturing 1/3 of the world's plastics. RTDs and your kitchen thermometer.